This is question 4 of the AQA GCSE Physics June 2015 Unit 2 question paper. On screen now is the mark scheme for the question, so please mark your work. Because the mark scheme is so long it's split over 3 slides, you may wish to pause the recordings to mark part A and part B of the question, and then move forward to mark the next few parts. On screen now is the first 2 parts of part C. Again, please use the mark scheme to mark your work, and then you can move on to the final part of part C, which is on the next slide. This is the final part of the question 4 mark scheme, so please mark this part of the question. Once you've finished that bit, if you got all of the question correct, suggest you move on. If you got parts of the question incorrect, or would like to listen to some of the explanation, please listen to the rest of the video to find out how to get that question correct in the future. So question 4a says a car driver sees the traffic in front is not moving and brakes to stop his car. The stopping distance of a car is the thinking distance plus the braking distance. What is meant by the term braking distance? So the braking distance is a distance a car travels. Remember, it's always a distance, not a time. People get confused there. Car travels under the braking force. That basically means that the force has been applied. That will get you 1 mark. For that question, you could also explain it as the distance the car travels after the brakes have been applied until the car comes to rest or comes to a stop. In part 2 of A, it says the braking distance of a car depends on the speed of the car and the braking force, and to state one other factor that affects braking distance. So braking distance could be affected by many factors. You're only looking for one. The first one that comes to my mind is the conditions of the brakes. So if the brakes are broken or aren't working effectively, or if they're worn, then that would affect it. But there are plenty of other ones you could have, such as the conditions of the road, whether it's been raining, or if it's icy as well. I've now just dropped in some other examples from the mark scheme. So you can see there: icy wet roads, worn tyres, road surface, the mass of the car and the passengers. So if you've got more people in the car, it's going to take a larger distance for you to come to a complete stop. The efficiency or condition of the brakes as well. Other things such as weather conditions, the gradient of the road, so obviously going to be harder to go down if you're going downhill. You'll take further to stop if you're going downhill. And also, you can see there, number of passengers, because that's going to increase the mass of the car. A part 3 says, how does the braking force needed to stop a car in a particular distance depend on the speed of the car? So here we're looking for a comment on both speed and distance. So the faster the car, the greater the braking distance. I should put BD. So the faster the car, the greater the braking distance. You must have a comment about speed and braking distance. So you could have said that as the speed of the car increases, the braking distance increases. But the idea that as one increases, the other increases, but there must be a comment about both speed, which I got in my faster, and also distance. That will get you 1 mark there. So in question 4b, figure 4 shows a distance time graph for the car in the 10 seconds before the driver applies the brakes. Use figure 4 to calculate the maximum speed the car is travelling at and show clearly how you work out your answer. So it's a distance time graph. And to get speed from a distance time graph, you need to calculate the gradient. So speed will equal the gradient. We want the maximum speed, so we want it when the gradient is the steepest. And you can see that the gradient steepest is a bit of a curve here to begin with, and then it straightens out over here. To work out the gradient, remember, gradient equal the change in y or the change in x. I've used a delta symbol to explain change in. So we need to find out the change in y and the change in x. To do that, we need to choose 2 points on the line. I'm going to choose this point here and this point here. So you can see that point there was one small square below 175, and you can see the y-axis goes up, each small square is 5, but if you've got 5, 10, 15, 20 and 25 there, so you're going to be 5. So I'll make the y at the top point will be 170. I'll shut this down here now. So my delta y equals 170 at this point here. Look at this point here now, minus, we can see it's 6, it's on 80, which gives me a value of 90. My delta x, if we go back to the top point, you can see that's on 10. And if we go back to this point here, it's 6. And that's going to equal 4. So your gradient or maximum speed equals 90 over 4, which equals 22.5 meters per second. Just to run through where you get the marks for that, you get 1 mark for trying to get the idea that it's the gradient and using numbers correctly or mistakenly from the graph, and the next mark is for getting the correct answer, which is 22.5. If you just did 170 divided by 10, so your answer around 17, that would have only worked out with that you got you 1 mark. Moving on to 4 part C, so the car did not stop in time. It collided with the stationary car in front, joining the 2 cars together. Figure 5 shows both cars just before and just after the collision. The momentum of the 2 cars was conserved. What is meant by the statement, momentum is conserved? Well, that is the conservation of momentum law, which basically means that the momentum before the collision is equal to the momentum after the same collision, and that there will get you the mark. In C part 2, it asks you to calculate the velocity of the 2 joined cars immediately after the collision using the correct equation from the physics equation sheet. So beforehand it's kind of given us a clue that we're talking about momentum. So if you go to the equation sheet, you'll see that momentum is equal to mass times velocity. We don't have the velocity afterwards, which is what we're trying to find out, and we don't have the momentum afterwards, but we do have the mass. The mass afterwards, because they're joined together, is going to be 1,500 plus 900. I've taken those 2 values from this before collision bit here. That gives me a mass equal to 2,400 kg. So that's my mass afterwards. In order to be able to work out my velocity, I need to work out the momentum afterwards. Now you got a clue to this in the previous question, because the momentum afterwards is equal to the momentum before the collision. So my P after is going to equal the momentum before. So I need to find out the momentum before the collision first. Okay. So I'm going to look back at the parts to begin with before. So you can see here that I've got a momentum of that car, or a mass of that car, which is 1,500, and it's travelling at a speed of 8 meters per second. This car here has a mass of 900, but it's travelling at 0 meters per second. So the momentum of this car is going to equal 0 kilograms meters per second, because it's not moving. and 900 times 0 is 0. The momentum of this car is going to equal the 1,500 multiplied by 8. I'm going to take this down here now. So we've got 1,500 multiplied by 8, which equals 12,000 kilograms meters per second. So now to work out V, I've got my mass from before, which is 2,400. I've got momentum, which is 12,000. Using this equation here, I can put those in. So I'm going to use the blue for that one. So I've got 12,000 equals 2,400 multiplied by V. So V is going to equal 12,000 divided by 2,400, and that equals 5 meters per second. In terms of where you get the marks, the first mark is for getting the momentum before as 12,000, that's 1 mark. For getting the mass is 2,400 is another, and finally getting the idea that it's 5 meters per second overall is a third mark for the 3 marks of the question. 4 part D says, since 1965 all cars manufactured for use in the UK must have seat belts. It is safer for a car driver to be wearing a seatbelt compared with not wearing a seatbelt if the car is involved in a collision. I want you to explain why, and the question is worth 4 marks. There are 2 ways to answer this question. It seems as though, considering what the question has followed on from, you've been talking about momentum. So the first method of answering the question is talking about momentum and changing momentum. So I've just dropped the mark scheme in here, talking about the momentum route through. So this is in terms of momentum. And you can see that the first thing is the idea that the seat belt will stretch. That means that the driver takes a longer time to slow down and stop, so that the impact takes longer. The second mark. It takes longer for the same change of momentum because you're going from whatever speed you're travelling at beforehand to usually 0 after the collision. And because that change of momentum takes longer, the overall force exerted on the driver is going to be less. That comes from the equation force is change of momentum over time. So you can see for the same change of momentum, if we make t bigger, we're going to reduce the force F. The next method for explaining why it's safer to wear a seatbelt is in terms of work done. Remember that work done equals force times distance. So force equals work done over distance. So if we start with the same 2 points that we've had before, or the same part that we had before, the seat belt stretches. By seat belt stretching, what we're doing is we're increasing the distance the driver travels. The same amount of energy is going to be transferred in the collision, so work done remains the same, but by increasing the distance we travel, we're reducing the force. So I've just dropped in the mark scheme for that part of the question. As you can see there again, seatbelt stretching, the distance travels increases, the same amount of work done as a result of the same amount of work done due to the equation that I've got up here. That means that if distance increases, the same value divided by a larger value is going to make a smaller value for the force, which is the final mark. And that brings us to the end of the question. So thank you for listening.